Hello viewers, welcome back after a long time. Today I will discuss about carbohydrate part 2, that is the isomerism in carbohydrates. I'll discuss in reference to the glucose because it is very important organic molecule, the carbohydrate in our body. Glucose has three structural forms, that is the straight chain or Fischer projection, then ring form or Haworth projection. Ring form is due to formation of hemiacetal bond in glucose, and in fructose we have hemiketal bond. Then chair or boat form. I'll discuss about this Fischer projection and Haworth projection. See, this is the structure of glucose. The C1, this is the C1, 2, 3, 4, 5th and 6th carbon atom. This aldehyde group, this oxygen is electronegative and this carbon is electropositive. This oxygen is electronegative. Say I'm taking the fourth hydroxyl group. Then this hydrogen is plus, this hydrogen has a plus charge. This oxygen has a minus charge due to the lone pair of electrons. So this carbon atom reacts with this oxygen or this oxygen, and similarly this oxygen reacts with this hydrogen or this hydrogen. So a structure is formed like this. I'm writing in a short form: 1, 2, 3, 4, 5 and 6, and this oxygen can react with this fourth or this fifth carbon atom. Similarly, in fructose, this C2 keto group can react with either this C5th hydroxyl group or C6 hydroxyl group to form this hemiketal bond. Next, coming to the chair or boat form. The chair form is more stable form and the boat form is less stable due to steric crowding. The chair form is more stable. How can you remember? In chair we are more stable, and that is the trick to remember it. Then coming to this isomerism. About this isomerism, lot of books given, lot of types, but Harper tells about the most authentic classification. So isomers, they have the same molecular formula but different structural formula. It may be functional isomerism, ring, stereoisomerism or optical isomerism. Functional isomerism may be of aldose, ketose, ring, pyranose and furanose form. Stereoisomerism, enantiomerism, D or L form. Then diastereoisomerism, that may be epimerism or the anomerism. Let's see one by one. First, about the functional isomerism. They differ in order of atoms. They have the same formula but the functional group is different. See, these are the structure of glucose and fructose. In glucose you will find a aldehyde group, and in ketose you will find a keto group. They have the different functional group, but the formula is C6H12 and O6 in both. Next, coming to the ring isomerism, the glucose has pyranose form and furanose form. As I have already told, glucose has hemiacetal linkage. See, this is the structure of the glucose. If this aldehyde group reacts with this C4 and this aldehyde group reacts with the C5, what will happen? We'll see. This C1 aldehyde reacts with the C4 hydroxyl group. We'll get a structure. We get a 5-member ring with the C5th and 6th carbon outside the ring. That will simulate a structure, the furan. So this is called furanose form. And if this C1 aldehyde group reacts with this C5th hydroxyl group, we'll get a structure like this, and C6th carbon will be outside the ring, and it will simulate a structure, the pyran. and this pyranose form is the most common form. 99.5% glucose remain in the pyranose form. Similarly, in fructose, this C2 aldehyde, this C2 keto group can react with this C5th aldehyde group or C6th aldehyde group. If C2 C2 reacts with this C5th aldehyde group, we will get alpha D fructofuranose, and C2 keto group reacts with this C6th hydroxyl group, will get alpha D fructofuranose form. And in glucose, in fructose, this furanose form, this fructofuranose form is more stable. Now coming to the stereoisomerism, they have the same structural formula but different spatial orientation. What is the requirement? That is a chiral or a asymmetric carbon atom. So what is a chiral carbon atom? A carbon atom with 4 different groups. The 4 different groups is called a chiral carbon atom. See, this is the structure of glucose. Here, if we take this C2, 3, 4 and 5, let's say this C2, we have 4 different groups attached to here, attached to this carbon, this portion as a whole. So this C2 is a chiral carbon atom or the asymmetric carbon atom. Similarly, C3, 4 and 5th carbon atom are also asymmetric or chiral carbon atom. Now coming to the Van 't Hoff's rule, it correlates the number of stereoisomers possible with the number of stereoisomers possible according to the number of asymmetric carbon atom, that is equal to 2 to the power n, where n is equal to number of chiral carbon atom or asymmetric carbon atom. So in glucose we have 4 asymmetric carbon atoms, so we have 2 to the power 4, that is the 16 stereoisomers possible. Coming to the enantiomers, they are mirror images of each other. Remember, En, entirely opposite of the molecule, are D and L isomers. According to the spatial orientation of H and OH groups on the penultimate carbon atom, we classify them as D or L isomer. If the hydroxyl group is on the right side, I'll say it is a D isomer, and if it is on the left, then it is a L isomer. So what is a penultimate or reference carbon atom? So this is the structure of a glucose. This is the last chiral carbon atom and it is called the reference carbon atom. So if the molecule, if the hydroxyl group is on the right side, then I'll say it is a D isomer, and if it is on the left side, and then it is called the L isomer. Though these molecules are entirely mirror images, but we take the reference of the penultimate carbon atom because we take the reference molecule as glyceraldehyde because it is the parent carbohydrate atom. See, this is the structure of the glucose, and this is the D-glucose and L-glucose, and D-glyceraldehyde and L-glyceraldehyde. In D-glucose, the hydroxyl group is on the right side, and in L-glucose, the hydroxyl group is on the left side, which is according to the reference of this D and L glyceraldehyde. Then coming to the diastereoisomers, stereoisomers that are not mirror images are called diastereoisomers. Let's say the D-glucose, mannose and galactose. They are not mirror images because see, lots of different molecules are there. So they are not exact mirror image, they are not entirely mirror image of each other. They are diastereoisomers. Coming to the epimers, if two monosaccharides differ in the configuration around a single asymmetric carbon other than the reference and anomeric carbon, this term is important, other than the reference and anomeric carbon. Example, glucose and mannose, they are C2 epimers, and there is enzyme epimerase which cause the interconversion. See, this is the structure of glucose and mannose. Let's say the glucose mannose are epimers around the C2, and here the hydroxyl group has a different orientation. Similarly, if I'll consider this glucose and galactose, they are different at the position of the C4 hydroxyl group. C4 hydroxyl group, they have different orientation. Now different epimers of glucose can be memorized with the help of a trick Maggie. M for mannose at C2 epimer, mannose C3 epimer is alloge, C4 epimer is, I have told, galactose, and C5 epimer is iodoge. Now coming to the ionomerism, there are difference in the orientation of groups around anomeric carbon atom. That is a new asymmetric carbon atom due to the formation of a ring structure. So how a new asymmetric carbon atom is formed? I have said already, this aldehyde can react with, say, this C5th hydroxyl group. What will happen? This becomes OH, H, then I'm writing in short form 1, 2, 3, 4, 5, 6, and this oxygen will form this bond. So a hydroxyl group is formed, a new asymmetric carbon, this one, because there are there are four different groups are attached here. So this C1 initially, which was not asymmetric, now become asymmetric. So if I write this in a Howard projection, what will happen? In the C1, this hydroxyl group will be present either in the above the plane of the ring or below the plane of the ring. If this hydroxyl group is present above the plane of the ring, this is called beta form, and below it is called alpha form. See, I have written this in the alpha ionomer, the hydroxyl group of the anomeric carbon is below the plane of the ring. How can you memorize? The beta would have been below, B for B, but the reverse occurs here. In beta form, the hydroxyl group is above the plane of the ring, and this beta form is more prevalent, that is a 62% of the glucose are in the glucopyranose form, the beta D-glucopyranose form. Then coming to the optical isomers, when a beam of plane polarized light is passed through a solution of an optical isomer, it is rotated either to the right, then it is called dextrorotatory, example is D-glucose, and if it is rotated towards the left, it is called levorotatory, the sign is given is a minus, then example is D-fructose. So don't be confused with the capital D and small d form. Capital D is for capital D and L are for the enantiomerism, and small d and small l are for this optical activity. So if they are in the equal concentration, there will be no optical activity, and that is called a racemic mixture. Now coming to some MCQs. When the glucose, so first about the glucose predominantly exists in which form? As I have already told, that is the beta D glucopyranose form, which is not an aldose. Glucose is an aldose, mannose also, fructose is a ketose, and galactose is also an aldose, glycerol is an alcohol. So answer is C and E. Which of the following are enantiomers? C, there would have been same name given. Here it is other name, galactose and glucose, so not, this is not. And D and L, no, small d and L are not enantiomer. Capital D and L should be written, and the same molecule should be written. So D and L mannose. Similarly, D glucose and L glucose. This has given small d and L form, so it is also not. So answer is C and E again. If you have any query, then write in the comment section. We'll do a lucky draw among subscribers, so please do subscribe, and thanks for watching.